So, we will continue about design and analysis of brake system. So far we discussed about the brake working methods. There we have seen the videos for both drum brake as well as disc brake system, and also we have discussed about various brake types, starting from drum brake, disc brake, then within the drum brake the 4 variation, right, leading and trailing, leading and S-cam and DO types. These are 4 types. Within that we are extensively focusing on brake drum as well as the disc brake system. So there the brake requirement aspect, brake torque requirement aspect we have done for drum brake system. Okay, we did even couple of problem also. Today we are going to discuss about a disc brake system. Right. In drum brake system we have discussed various aspects, right. Remember there is a term called self locking, that we have discussed, and self locking also we discussed, and what are the terms we had in leading and trailing. Activation force, right, the activation force P equal to Mn plus or minus Mf by C. This is the equation. Depends on the, if it is a plus for the trailing, minus for the leading, right. This was discussed, we have done that. Now we will go for a disc brake system, right. In disc brake system I have seen this is a typical disc brake system where you have a rotor or disc, right, and this is generally called as a caliper. So caliper fitted with the piston. So you have a brake line material, either you can have a circular shape, button type, this is called button, circular or button type. Sometime you may have its annular type. Hey, this is called, I am just giving you just information. This is annular type. So 2 variation you can see from disc brake aspects. We will see that. So this is the arrangement, which a rotor is given here. Then the brake parts here, maybe it could be disc type, circular type, if not annular pad. Okay. So as you apply a brake through pedal, right, through vacuum booster, the master cylinder activated. From the master cylinder the brake fluid goes and comes in this direction. Then this pushes your piston, right. This is pushes your piston. Since the caliper has a self adjusting mechanism, this has a self adjusting mechanism. Okay, it has self adjusting mechanism. Because of that, the moment this one piston pushing this way to this pad, the other side also, the pad also will try to move. So they move equally and make a contact against the rotating disc. This is how this disc brake system functions. Maybe I will have a couple of slides which give you a clear cut information. The caliper squeezes pads to create a force on the surfaces of the rotor. They use in most automotive application. Benefit is, it's a simple design as I explained, self adjusting caliper, and rotor venting allows faster for heat dissipation. Okay. More importantly, do we expect any self locking in disc brake system? Self locking. Yes or no? No self locking, in fact. So that is the advantage. No self locking, because there is no leading and trailing arrangement, right. There is no leading and trailing arrangement. If you have, then that is comes into picture. since there is no need of a leading and trailing shoe arrangement, just a button or annular pad which is going to press against the rotating disc. So fine, this is much better. Okay, perhaps we will discuss more in detail. There is one term is called braking factor, BF. Okay, a braking effort or braking factor. There we will discuss in detail how this is useful, particularly for a brake dynamics aspect. Okay. You can see the same what I have discussed just now. This is given in the schematic diagram. The first step is, you can see that this is the rotor and you have a pads on the both side attached with the caliper, and this is the piston, the brake fluids comes here, right. When the force is applied by driver to the master cylinder, then the pressure from the master cylinder causes one brake pad to contact rotor. That is the second stage, you can see step 2. Then the step 3 where the caliper then self centers, causing the second pad to make a contact. This is happening everything with a fraction of seconds, right. What will be typical braking time you would experience? Is it few seconds or a few minutes, or what is that? Few seconds, right. So the entire operation would happen within the couple of seconds. Now we will discuss what would be the torque, right. Similar to the drum brake system, we here also will discuss what would be the torque for a disc brake system aspect. And this is the geometry you could see here, where this is the rotor, these are the brake pads. Okay. In fact, the brake pad is the annular pad. This is the, in fact, the annular type. Annular type. So you could see there are the notations. P is the force on the pads, theta 1, theta 2, and Ra are not dimension of the brake pad. That means I would say that Ra is the inside diameter, inner diameter, maybe inner radius more appropriately. Okay, Ro, outer radius, right. Then theta 1 is the angle from the center where the brake line starts. You can see this. This is your theta 1, similar to the your drum brake system. Okay, and theta 2 is the actual angle from the center to the end of the brake line. In fact, you need theta 2 minus theta 1. That's a one will give you exact contact, right, for the brake aspect. So that will be the contact angle. Okay, this is the diagram taken from Design of Machine Elements by Bandari McGraw-Hill. So you could refer the textbook also. In fact, we try to understand how the force is going to be, right. So the force will be here. Then when you apply the brake thing, how the force is going to happen. What we do, so we will take the small strip from here and try to do the integration, and from there we will find out what would be the torque, right. This is a d theta. So I am not going to explain about derivation, because the derivation is there in the already textbook, right. To save time period, I straight away give the equation, from there we will solve. Okay. And this is the pressure, you can see the pressure vary from internal diameter Ri to R0 and theta 1 to theta, Pr, Dr, d theta. Okay. And this would be constant, right. The d theta minus theta is constant. Similarly, if the moment pressure into, right, another this is the not pressure, this is the force. Pressure into area would give you the force aspect. Similarly, the force into distance would give you a torque activated in the disc brake system. So, when we talk about torque, we always talk about MT is a torque is nothing but frictional torque, right. We are talking about everything happening due to whatever the energy, right, the kinetic energy need to be converted into heat energy or frictional energy that happens due to your friction. So, mu is your coefficient of friction, mu is your coefficient of friction, right. So, this is the equation Pr square dr you can see here. Then pressure is clearly given, inner outer radius, initial and final contact angle, coefficient of friction. Finally, you would expect this equation simplified one as this, you can see that. Now, I will give you two information from before proceeding to find out actual pressure, actual torque also. Okay. In not only disc brake system and also clutch, we propose two different theories. One is called uniform pressure theory, the other one is called uniform wear theory. Okay. So, what does that mean? Uniform pressure theory and uniform wear theory, right. So, assuming that, so when your rotor is there brand new, the pad is applied, what do you expect the contact? The contact will be a complete uniform contact. Okay. So, the entire surface of the brake pad will make a contact against rotating disc. So, in that case, that is called uniform pressure theory. That's a uniform pressure theory. So, you are assuming that you allowing the brake system to run for certain time. After some time, what do you expect on the brake pads? Do you expect the brake pad is uniform, or is there any changes? Yes? Sorry. Wear will be there. Obviously, you will have a wear. Okay, because of wear. So, what do you expect? The contact will be uneven. The contact will be uneven. Okay. So, what happened? If the inner radius, the pressure will be higher, the outer radius pressure will be low. It will fall like a parabolic curve. Okay. Maybe I will discuss those things when we go for a clutch aspect. Okay. So, that causing again not inequality, which again keep changing, rubbing the pad and the disc. So, at fine time, the wear will be uniform across the contact area. Okay. That is the reason. So, we will have a uniform pressure theory one thing and uniform wear theory another thing. Okay. Let me ask one question, in which theory the torque will be more? Is it uniform wear theory or uniform pressure theory? Yes? Pressure. Torque will be pressure will be more in uniform wear theory. Okay, we will see that anyway. Okay. So, one more thing, let me ask question. As a diesel engineer, what would be your criteria? You want to operate for a maximum allowable torque or lesser than torque? Yes, just think about that. So, those things we will discuss, okay, as we progressing in the lectures. So, this is the equation you can see here. So, when the brakes are new, the pressure, allowable pressure is uniform across the contact area, then you will get the corresponding pressure force equation, and this is your frictional torque equation. And if you solve it, finally you would expect, right, this is the equation you get, this is the pressure equation, and I think something happened here. I will rewrite again that equation, I will rewrite. I will do that, yeah, you can see here. Now, we will move on to the uniform wear theory. I will come back to that point aspect. So, with the older brake pads, axle wear can be assumed to be constant. the pressure is expressed as the maximum allowable pressure which occurs at inner radius RA. Obviously, smaller the area, pressure will be higher, right? Smaller the area, pressure will be higher. So, the force will be proportional to your inner radius and outer radius with the allowable pressure. By again, if you solve the equation with the integration, finally you would expect your force equation. You can see that this is the force equation, the corresponding the torque, frictional torque, you could see this mt equal to mu p by 4 d plus d, where area equal to theta by 2 d square minus small d square by 4, okay, where please understand the theta in radians. This is the equation you have to utilize if it is uniform wear theory aspect, right. So, in general we will move on to the, irrespective of whether you use a uniform pressure theory or uniform wear theory, the frictional torque will be mu into P into Rf, whereas Rs is the frictional radius or friction radius. That radius will change for both uniform wear theory as well as uniform pressure theory. Look at this, Rf equal to d by 4, which is for the uniform wear theory. Of course, d is your outer dia, similar to the d RO, okay, and small d is the inner dia, okay. And the moment you go for a uniform pressure theory, the Rf would be d cube minus small d cube by 3 into d square minus d square. This is what happened. So, same thing you can represent in terms of, right, Rho square, Ra square with the radius also, sorry, this should be cube and this is square minus Ra square. This is the way also you can do that. And pressure P equal to, sorry, this is allowable pressure, okay, and the force acting on the brake pad P equal to your allowable pressure into the area. Already we know what is the area. If it is a button pad, straight away pi d square by 4, that is you can do that. If it is annular pad, theta 2 minus theta 1 into that area things, that is what is coming, okay. So, this is the torque requirement for disc brake system when you use it uniform pressure theory and uniform wear theory, okay. And probably we can do some problems also in this regard. Before going to the problem, there is one more information I would like to give. You can see that there is an interesting information, okay. This is your rotor or disc, vice versa same, okay. Do not confuse when I say disc or rotor, both are same. Right, and this is your button pad, right. So, the eccentricity also will play a vital role. So, it depends on where do you want to keep it, the button pad from the center of the rotor, that will alter the pressure variation, okay, that will alter the pressure variation, where R is the radius of the pad, E is the distance of the pad center from the axis of the disc. So, this is the relationship. In fact, this give you the information about the ratio of the pressure things. You can see that the friction radius Rf equal to delta by E, okay, and R by E, that is given the how much variation you can do that, right. So, as you increasing the R by E ratio, the friction radius again decreases. As the friction radius decreases, the ratio between the maximum pressure to the average pressure also inversely proportional increases. That is what you would see that. This is taken from the reference of on circular spot brakes, okay, from GA Physics C of transaction of ASME Journal of Engineering, Engineering for industry. So, this is the reference I have chosen. What do you understand? What do you understand from here? You have a rotor here, right, then put the pad, as move the pad from the center to away from, what do you think? What is happening? Let me ask question. If the pad is matching with the disc axis, what happened to the pressure? It will be maximum, right? As we move on to away from the center of the disc, right? If you move on, this is the first position, assuming that this is my rotor, this is axis. So this is my first position, this is the pad, right? Another scenario I will give you. This is the second scenario. Tell me, where do you expect the pressure variation? Right. Maybe you can refer this paper, that will give you more information. Okay? Yeah? Right. Can we do a problem, please? Following data is given for a caliper disc brake with the annular pad for the front wheel of the motorcycle. The torque capacity is given as 1500 Newton meter. Outer radius of pad 150 millimeter. Inner radius of pad 100 millimeter. The coefficient of friction mu is given as a 0.35. The average pressure on pad is 2 megapascal. The number of pads are given by two numbers. Calculate the angular dimension of the pad. It's a small problem. Okay. So we have a caliper disc brake with the annular pad. Okay. The torque is given 1500 Newton meter. Right. The dimension is given, both inner and outer. Radius of the pad is clearly given. The coefficient of friction also given, and pressure is given. Average pressure is 2 megapascal. The number of pads are 2. Okay. So I have to find out only the A, the annular area of the thing. It's a simple thing. Okay. What pressure theory? What theory we can we use? Is a pressure theory or uniform wear theory? Which one can we use it? Yeah? Yes? Pressure theory. Okay. It didn't say anything. It's a brand new or uniform theory. It didn't say anything. So we can go for straight away with the uniform pressure theory. We will use the uniform pressure theory. So MT is given, right? MT given is 1500 Newton meter. This is for how many pads? For 2 pads, right? So how about for 1 pad? Per pad? The MT would be? Tell me how much would be? 750, right? 750 Newton meter. That will be the things. Okay, that's one thing is there. Then you have RO is given 150 millimeter, RA is given 100 millimeter. Okay. Then mu is given as a 0.35. Then P, the pressure P, okay, 2 into 10 power 6 Newton per millimeter square. Yeah. Okay. So clearly given. Now we need to find out what is the equation we have. General equation, MT equal to mu into RF into P, right? P is the force, RF is the frictional radius, mu is the coefficient of friction. Okay. So which is known to you? MT is known to you, right? Torque is known to you, mu is known. Okay. And which is unknown for you? P is unknown for you, right? That we need to find out. Okay, that's we need to find out. So for uniform pressure theory, what would be the RF? RF, RO cube, RA cube, right? RO square minus RA square 2 by third. This is your RF. Can you tell me what will be the RF for this? You substitute, already you know that what is the RO, what is the RI, right? And if you substitute, can you tell me what would be the value of RF, frictional radius? So, are you getting RF equal to 126.67 millimeter? Are you getting this value, right? That's fine. Okay, excellent. So, now we need to find out the force acting. So, MT equal to mu RF and P. So, substitute, this is 750 Newton meter. Yeah. So, make it everything in terms of Newton meter. 750 equal to 0.3 and 126.67 into 10 power minus 3 for the meter, okay, into P. So, what is the force is acting here? So, we are doing for the one pad, please understand, okay. The entire torque 1500 Newton was given for the 2 pads. So, per pad how much is going to be? Half of that, right. So, what is the force are you getting? Are you getting 16,916.85 Newton? Okay, you would expect 16,916.85 Newton, that should be there. Okay, so that's a pressure. Sorry, I'm sorry, that's a force. So when you say force, okay, we want to know finally we need to find out the area also. So allowable pressure, we know that PA into area, right. What is the PA is given for us? 2 megapascal, right. That was given in the problem, 2 megapascal. So 2 into 10 power 6 Newton meter square. I think I made a mistake earlier. I said Newton millimeter square. Supposed to be Newton per meter square, I guess. Yeah. Is it my dimensions are correct? No, 10 power 6 Newton per millimeter square or meter square? Meter square. Okay, for 2 megapascal. Right. So can you give me what is the area now? We are getting the area. Eight. Okay. Millimeter square. Okay. So 8458.42 is right. 8458.42. We are getting millimeter square. Millimeter square. There, yeah. That's your area. Okay. That's clearly given. So now we want to know, this is your annular pad, right? This is a theta, yeah. This is the theta thing. So what is this actually? This value? Ri R1, doesn't, either way you can say that, and this would be your RO. So what do you expect the formula? The area would be half of, this would be theta, right? Theta RO square minus Ri square, right. So that should give me in terms of radians. I will rewrite A equal to theta by 2 RO square Ri square. Substitute, can you tell me what is the theta are you getting? Are you getting 1.3533 radians? Yeah. Are you getting 1.5 1.3533 radians? Okay. In terms of degree, it should be 77.54 degree. So that is some fraction. So in manufacturing it will be difficult. You don't want to have it. So what you could do, you can make it a round off to 80 degree. So the annular pad size would be 80 degree. This should be your answer. This is your answer. Okay. Any doubt in this problem? Right. Shall we move on to the second one? Yeah. Yes. So you have another problem. A button pad disc brake uses dry sintered metal pads. The pad radius is 12 millimeter and its center is 45 millimeter from the axis of rotation of the ATM diameter disc. So that's also given. Using half of the largest allowable pressure, the P max would be 2.4 megapascal. Find the activating force and the brake torque. The coefficient of friction is given as 0.31. Okay. So this is very different from the previous one. The previous one was annular pad, whereas this one is a button pad. That's a difference. Okay. What information we have now? Right. The pad radius given. R is the pad radius. R equal to 12 mm is given. Okay, that is clearly given. Fine. What is this 48 mm? 48 mm from the axis of rotation of 88 mm disc is clearly given. E value exactly. So the E value is given 48 mm. Okay, that's clear. That's fine. Then what is 88 mm? That's a disc diameter. Okay. Yeah, disc diameter capital D, you can say that. Okay, capital D is clearly given, 88 mm is given. Okay. And P max clearly given. P max given as a 2.4 megapascal. Okay. And mu is given as 0.31. Yeah, that's a thing. Okay. So we need to find out the RF. That is a very important thing, right? So if we want to find out what is the equation RF equal to, RF equal to delta star E, right? That's the equation. That's what. So let's see. So the friction radius R equal to delta star into E. This is the equation. You can see that. So which one? What is the R you are getting now here? R by E. Can you tell me what is R by E value? R equal to 12. This is 48. That should give me 2.5, right? That should give me 2.5. Sorry, 0.25. Yeah, sorry. I mean to say 0.25. Right. You have the value 0.2. Right. You have the value for 0.3. So you have to do the interpolation. Right. If you do the interpolation, okay. So for R by E equal to 25, right, from the table, using this table, right. So you would expect the delta would be 0.963 after the interpolation, please. This is 0.963, right. So 0.963. The corresponding, the P max by P average, okay, equal to 1.290. This is between these two areas. So now we have taken the R by E interpolation 0.2 to 0.3. We got this value 0.963. The corresponding P max by P average is given 1.293. Okay, 1.290 is clearly given. The question is, what is the question? Half of the maximum pressure, right? That's what clearly given. It's given half of the maximum pressure. That's what we need to find out. Yeah. Okay. So now we know the values here. So our intention is we need to find out, right. So we need to find out the MT equal to mu into RF into P. This is what we need to know, that ultimately we need to find out what will be the activation torque. That's it, that's a thing. Okay, that's clearly given. So the RF would be what happened RF for this disc brake aspect, delta E, right? Straight away you can do delta E also. Delta E also we do that. Delta, okay. We got, what is the value delta? 0.963. 0.963 into 48. The RF gives me 46.2 millimeter. That's RF. That's RF. Then we need to find out the average pressure, right? The average pressure we need to find out. What is the average pressure? P average is given half of the P max. That's what we need to know, that half of the P max, right, divided by whatever you found out the value 1.29. So with that you would expect this should be 0.155 megapascal. Okay, the pressure P, the force equal to pi r square into P average, which is what we are getting here. P average we know that. So pi into, what is the R value? Your R will be 12, right? Button. It's a button type. 12 square, right? Into, straight away I multiply in terms of millimeter 1.55. If I do that, that's give me 70 Newton. Okay, that's give me 70 Newton. This is for the one side alone. We are talking about one side pad, one side pad. Yeah. Then the brake torque, MT equal to mu RF, the force 0.31 RF, already we know that, right, 46.2, then 70 Newton. So that's give me MT equal to, how much you are getting? 1000.2 Newton millimeter. So this much torque is produced if you use the button brake system, right, in that within the disc brake system. I think I'll stop now. Okay, tomorrow onwards we are going to important topic, dynamics of brake system. That is very critical one. Okay, this one is gives you understanding about what you have learned during your undergraduate. Okay, so undergraduate would have done the basics of disc brake, drum brake, right, the torque aspect. Okay, so now you know that how torque is applied through activation force in the drum brake and also through piston, right, through caliper system to the rotor disc in the disc brake system. That you understand how this torque is going to affect the dynamic analysis. Then what are the dimension of the vehicle system play a crucial role. Okay, that also we are going to discuss, and also we are going to discuss when the moment you apply a brake, how much mass is going to transfer from rear axle to the front axle. That is also we are going to discuss. Then when mass transfer is transferred, then how to optimize the braking effort. Remember, we need to have more braking effort at the rear front axle than the rear axle. So how to optimize this in the dynamic analysis, the braking proportion aspect. Okay, that's one thing. And also how to design such way that we want to have one particular axle, either front axle or rear axle. to control the motion of the vehicle, right. That is also we are going to discuss. So, for everything, right, whatever we discuss, right, it start from the basics of the dynamic analysis, so, but tomorrow. So, that is why do not skip it, try to attend, it will be very interesting. Okay. We will discuss so many aspects. So far you know mu equal to coefficient of friction of your brake lining, right. Then you will have a mu equal to the rolling radius, that is also come into picture. Then you have a mu s equal to your road friction, those things will come. So, we will try to find a relationship between these three, right. So, it will be very interesting. Okay. Yeah, thank you.